Hi everyone, we'll talk about constitutive modeling of particle field soft composites for soft robotic applications.
Last quarter, we built a soft robot designed to climb pole. This robot is made with EcoFlex 30 and EcoFlex 50 parts. Due to its low stiffness, it will only climb to 45 degrees.
In this project, we will characterize particle field EcoFlex 30 composites at different volumes and strain rates in natural tension, and compare to muscle tissue to identify best material to try next.
EcoFlex composite were tested under uniaxial tension with an instrument machine. We got the force displacement data from the testing and we convert them into stress and stretch data for model training.
We extracted different types of muscle data from literature, including rat muscle, pig muscle, and human muscle. As their data points were in Cauchy stress, we converted them to Piola stress. Our architecture is based on one important physical assumption. EcoFlex composites and muscle tissue are perfectly incompressible and isotropic. The input can be further reduced to a set of only two invariants. We train our model using MSE loss, which penalizes large errors. We used R2 values as our evaluation metrics.
In experiment 1, we ran baseline training with all terms active in the architecture on our composite data. After that, we then used the models trained on the lowest strain rate to predict the higher strain rates within the same EcoFlex volume, confirming that the model can closely predict higher common strain rates. We then tried different traditional models for rubber to approximate the elastic modulus from the weights. The first one is the neo-hook model, which uses only the first invariant term as shown in the equation on the left. Overall, we see R2 values all above 0.94. Thus, we expect a reliable G and E estimates from this model. We also tried Blasco model, which uses the second linear invariant term. We can see the model overshoots at the beginning and then undershoots towards the end, because the CAN is trying to minimize the error between prediction and data. Lastly, we tried the Moni-Rilvan model, which combines both, and we see that overall neo-hook performs the best. We apply Hosfeld and neo-hook model on the muscle tissue to extract model parameters. We approximated E from model parameters and compare against pure EcoFlex using neo-hook estimates due to its better fit. We do the same with the muscle tissue using neo-hook model, and see that all muscles are less stiff than volume 30% composite. Additionally, human muscle is less stiff than pure EcoFlex. We will discard both terms from future comparison.
Finally, we used our models trained on composites data to predict the muscle tissue without L1 penalty and with 0.001 and 0.01 penalties to prevent overfitting. This to compare volume 10 and 20% composites to rat and pig muscle structurally. At 0.01 penalty, we see model output simplified to only 1 to 3 discovered terms, but some being driven nearly to 0, resulting in significantly poor fits. Overall, we see better fit in pig muscle predictions, with models trained with volume 20% composite data performing best. In conclusion, our study suggests that the composite with 20% volume added particles is structurally more similar to muscle tissue, especially at lower strain rates and to pig muscle, with average R2 values of 0.7. Based on our obtained E value from neo-hook model shown previously, this composite is 154% stiffer than pure EcoFlex 30 and 51% stiffer than EcoFlex 50, thus selecting it as an alternative material to try for our next robotic prototypes. For limitations, our muscle data collection was extracted from literature using digital tools. Also, soft tissues are naturally heterogeneous, which might impact data collection and the results of our model.